for ongoing discussion of the environmental impacts of travel to meetings and observatories, education and outreach about sustainability, and using our scientific expertise to inform public policy on climate change. Speaking of which, I want to mention the AAS Council this morning discussed issuing a public statement emphasizing the importance of fully incorporating scientific knowledge in public policy, such as EPA and DOE, subject of great concern in today's political climate, the growing skepticism of science and the scientific process. At the suggestion of the Sustainability Committee, the AAS has recently added an option on the meeting registration form where you can buy carbon credits to offset the greenhouse gas emissions associated with your travel here. One round trip coast to coast by jet plane produces about 1 ton of carbon dioxide per person, currently priced in the CO2 market at about $50. If you opted to pay that surcharge, thank you. And if you didn't, please consider it next time. We're now vetting the available options for where best to invest the funds collected. Previous special sessions of the Sustainability Committee have included science review talks by prominent climate researchers, education, how-to workshops on bringing climate change into Astro 100 classes, and role-playing practice for conversations with climate deniers. Today's session focuses on one issue and is centered around one question: geoengineering the atmosphere to fight climate change. Should astronomers worry about it? I'm going to assume that everyone here knows what global climate change is and why it's important. But maybe not everyone knows what geoengineering is. Geoengineering is a large family of ideas and proposals that have been floated in recent years to address climate change by intentionally changing the Earth's atmosphere so that either CO2 is reduced or else incoming sunlight is reduced. An example of ideas to reduce atmospheric CO2 is carbon sequestration, or pumping carbon dioxide underground. Ideas to reduce incoming sunlight include inserting some type of aerosol particles, such as sulfur dioxide, into the atmosphere, spraying large quantities of seawater droplets to create artificial clouds, and launching mirrors into orbit. It's these proposals, above all, we wanted to address today because of their obvious potential impacts on ground-based astronomy. But we are also keen to discuss the feasibility, the cost, the possible unintended consequences, and the ethics of intentionally changing our only atmosphere on a global scale. The format today is a panel discussion. Each panelist will get roughly 5 minutes to make some introductory remarks. I will then serve as moderator of a multi-way conversation. We invite the audience to supply questions as well. Brian Miller there is at the door, is handing out paper, and will collect your questions if you have them mid-session for us to sort through in real time and pass on to the panel. We'll also try to reserve some time for general free-form question and answer at the end as well. We are live streaming on Facebook, and we are recording the session, and we plan to post the videos on our website as well. I'm delighted now to introduce to you our 4 panelists. Professor Tom Ackerman is Director of the Joint Institute for the Study of the Atmospheric Ocean and Professor of Atmospheric Sciences at the University of Washington. His primary research interests relate to the processes that control energy flow into and out of Earth's climate, such as clouds and aerosol, as well as remote sensing of atmospheric processes. He's the recipient of the NASA Distinguished Public Service Medal and the Leo Szilard Award for Science in the Public Interest, awarded by the American Physical Society. He's a Fellow of the American Association for Atmospheric Science and a Fellow of the American Geophysical Union. Dr. David Grinspoon is a Senior Scientist at the Planetary Science Institute, and my apologies about his affiliation planetary spacecraft missions for NASA and ESA, the Japanese Space Agency. In 2013, he was appointed the inaugural chair of astrobiology at the United States Library of Congress. He studied the human impact on Earth systems and organized a public symposium on the longevity of human civilization. Grinspoon's popular writing has appeared in Slate, Scientific American, Natural History, Novelist, Astronomy, Sea, Boston Globe, LA Times, New York Times, and Sky Telescope. He's the author and editor of several books. His new book, Earth in Human Hands, was named a Best Science Book of 2016 by National Public Radio. Grinspoon has been recipient of the Carl Sagan Medal for Public Communication of Planetary Science by the AAS. Dr. Jane Long recently retired from Lawrence Livermore National Laboratory, where she was Associate Director for Energy and Environment. She served as the Dean of McKay School of Mines at the University of Nevada, Reno, and was a scientist and department chair in energy and environment for Lawrence Berkeley National Lab. Since retiring, Dr. Long has been serving as a senior contributing scientist for the Environmental Defense Fund. She's also been a visiting researcher at UC Berkeley. Dr. Long's current work involves strategies for dealing with climate change, including reinvention of the energy system and geoengineering and adaptation. And last but not least, Professor Mel Ulmer, Professor of Physics and Astronomy at Northwestern University in Evanston, Illinois. Professor Ulmer is a fellow of SBIE and the APS, as well as a twice-over NASA Innovative Advanced Concepts Fellow. He's well-versed in scientific space satellite technology and was co-investigator to two NASA satellite experiments, OSO-7 and CGRO. He's an expert on X-ray optics and has since 2014 extended that expertise to normal incidence for UV visible applications. He's also worked on numerous photon detectors for the X-rays through the near infrared. It was an email from Professor Ulmer to then AAS President Meg Urey several years ago about the possible effects on ground-based astronomy of geoengineering the atmosphere that planted the seed for this special session today. All right, let's get started. So each panelist will have about 5 minutes to make some introductory remarks, starting with Tom Allen.
Thank you. It's a pleasure to be here. I'll apologize in advance that my voice is a little raspy. It comes from hanging out with my granddaughter over Christmas and her passing a cold along with me. It's a little unusual for me to be at an Astronomical Society meeting. I've never been to one before, but I have published a paper in the Astronomical Journal. And I did start my career in planetary atmospheres, and I talked to the exoplanet people, so maybe there's a few connections. I'm going to talk very briefly about solar climate engineering. As James mentioned, there's also the idea of carbon dioxide removal, which I will not talk about. I'm going to talk about solar climate engineering because it is my expertise, but also because it is a technology that is much more ready to be deployed potentially than carbon dioxide removal. I want to remind you of the atmospheric greenhouse effect. Most of you are aware of this, but I want to point out the two numbers at the bottom. The surface of the Earth receives roughly twice as much energy on an annual average basis from the atmosphere than it does from the sun. So small changes in the greenhouse effect have large changes in the climate as we know. These are projections from the IPCC. You can see in the red circle that the temperature change is estimated for the next decade go from 1.5 to 5 degrees, where those bracket emission scenarios, which are sort of business as usual in the pink, and a drastic reduction of emissions in the blue. In the COP21 Accords in Paris, it was agreed by the nations of the world that we would strive to keep the change in temperature to 2 degrees or less above pre-industrial, and that we would actually target 1.5 degrees. So if I go back for a moment, you you can see that we have work to do if we're going to keep it under 2 degrees, because the trajectory we're on at the moment is 5 degrees by the end of the century. So, my conclusion is it is not possible to meet that 2-degree goal without either immediate drastic reductions in emissions or the use of solar climate engineering. This is not an argument for or against it. It is a matter of looking at the climate and the emissions trajectory we were on. There are various methods that have been talked about for solar climate engineering, and I've outlined them in the red box up above. Although people have talked about space mirrors, the space mirror technology is a little troublesome, so I'm going to ignore that as well. And I'm going to focus on the two that we've actually talked about. One of them, both of which have natural analogs in some sense. We are familiar with volcanic eruptions. We know that volcanic eruptions produce aerosol clouds in the stratosphere. Those clouds reduce the temperature of Earth. We have very good measurements from the only recent large volcanic eruption of Mount Pinatubo in 1991. I might add that my one astronomical publication with the late Jason Cardelli was looking at astronomical data and inferring the size of volcanic particles from attenuation of telescope data. We also know that ship tracks, if you look at the picture on your right, that ship tracks in marine clouds are produced by the emission of engines, ship engines, and we know that they cause brightness. We have a number of examples of this, but I can show you many more. So these are the two techniques we're talking about: creating synthetic volcanic clouds or creating brighter clouds over the ocean. There are positive and negatives associated with each. So let me give you the, this isn't even 30,000 feet, this is at least 60,000 feet view. What do we know from model studies? We know that solar climate engineering can be used to reduce global warming. But we have to choose the climate that we want, because when we reduce solar radiation to compensate for greenhouse warming, we don't balance both temperature and precipitation. The temperature, the water vapor cycle wants to slow down when you reduce incoming solar radiation. So if you get the temperature right, you will reduce global precipitation. So in some sense, if we're going to do this, we're going to have an argument about what climate do we want to have and who gets to decide what climate we want to have. Coupled into all of this is a large and complicated subject of regional variability in climate. Under all the scenarios that I looked at, the Arctic still wants to warm. And I can explain the physics of that, but I'm just going to go on. It will happen given these kinds of risks. There are also potential impacts on regional hydrologic cycles such as the monsoons. And those are much more problematic, much harder for us to analyze at this point. Okay, a very abbreviated list of some things that we've done. One of these is a technical engineering problem. Both of these techniques require the generation of lots of small particles. We're talking in marine cloud brightening work that I've done about 10 to the 15 particles per second to create the equivalent of one ship track. So there's a lot of particle generation that needs to be done. It also involves processes that we don't understand all that well in some cases. We don't know what will happen with these additional particles. Will their injection produce unexpected consequences? That's a long and complicated subject. I think there aren't as many unintended consequences as you might think. There might be, but I could be wrong. And then again, there's this whole issue of what are regional consequences and who are affected by those regional consequences, and how do we view that in the sense of social justice. Resolving these questions require, the sort of technical and science questions requires at least a decade of process-related research. Sometimes when you read the literature, you get the assumption you can go out and start this tomorrow. We can't go out and start this tomorrow, at least not in a responsible way. And we would probably need another decade after that in order to get to the point of being able to deploy systems. I want to briefly reframe the problem. We have a conjunction here of science, ethics, and governance. The ethical issues for research are different than those for deployment, and for those of us sitting in this room, many of the issues are really about research. We cannot start solar climate engineering by definition means we have to have a way of getting rid of CO2. It's a very complex issue of ethics and governance and how they interact with science, and much of this has not yet been explored. My position here is that I'm an agnostic regarding the deployment and the use of solar climate engineering. I firmly support the need to do the research because I believe the information is necessary to separate the workable ideas, I'm trying to find the right word, the workable ideas from those that are simply out of the sky. I was sort of dragged into this kicking and screaming, but have found it to be intellectually challenging, as well as broadening my own sense of how ethics and science interact. Thanks.
Thank you, Tom. And next, we'll hear from David Grinspoon from the Planetary Science Institute. Oh, you can stay there if you like. As you like. I'll do this. Okay.
We're going to lose the panelists on that thing.
It's not going to be me.
I don't have any slides. I'm going to talk and gesticulate wildly. I do have a prop I'll get to. The question was, should astronomers worry about geoengineering? I'm not going to talk about the obvious reason why astronomers should worry about it, which I imagine we'll get to, which is that if we put a bunch of junk in the atmosphere, it's going to scatter light, make it harder to see the rest of the universe. I imagine that will come up. But I'm going to say, yes, astronomers should worry about geoengineering for two other reasons. I'm start my little timer here so that if I get carried away, I'll bring myself back in. For one thing, it's an astronomical problem if you define astronomy broadly enough to include planetary science and planetary evolution. It's a problem of planetary radiation balance and what mechanisms might affect that here and elsewhere. When I was a postdoc at NASA Ames studying planetary atmospheres, my two mentors, Jim Pollock and Carl Sagan, were working on a paper about planetary engineering. And in the same paper, they considered terraforming of Mars and Venus and other worlds, and also the potential engineering of Earth. Physically, it's all the same problem. How would you consciously intervene in planetary evolution? What are the levers you could pull? How would you maintain stability? All of that. So in that sense, it's an astronomical problem. It's also relevant to cosmic evolution, or what is now sometimes being called big history. And my recent entree into this subject is that a few years ago, I was selected to be chair of astrobiology at the Library of Congress, which, by the way, is a relatively new position, and it's a wonderful opportunity. And if any of you are interested in spending a year working on a problem on the intersection between astronomy and humanities, I urge you to look into the chair of astrobiology at the Library of Congress. They're looking for new applicants, and it's really a tremendous experience. But the proposal I wrote that was selected was called Astrobiology in the Anthropocene Era, Exploring the Potential Roles of Life and Intelligence on Earth and Beyond. So I proposed to look at the Anthropocene, which is what geologists are now arguing about, a term that they're arguing about, which has been proposed to represent a new epoch in the geological timescale, characterized by a new force, a geological force, which is the combined effects of humanity changing the planet. And I propose to look at that question from an astrobiological lens. And I'm going to put in a little plug here that work has recently, as in the last couple of weeks, produced a book that just came out called Earth in Human Hands, which is a summary of my thoughts on this question of the Anthropocene, seen from a sort of cosmic perspective. So if you're interested in this topic and what I have to say, there's a lot more detail in 500 pages than I can say in 5 minutes. But my perspective on geoengineering is an evolutionary one. I believe that the beginning of a time when cognitive processes becomes a key part of the way a planet functions is potentially as significant as the dramatic planetary changes marking the other 3 eon boundaries in Earth history. The other 3 eon boundaries, to put it very crudely, were the origin of life, when life took over the biosphere chemically, and when life became complex. And I propose that we are potentially at a new eon boundary that is that significant when cognitive processes have become planetary processes. Now, if the Anthropocene is really to represent an eon boundary, the beginning of what I wishfully call the Sapiezoic, then it implies a permanently changed planet. That it implies that self-aware geological change will, for the rest of the life of the planet, will be to some degree controlling the planet. But that can only be the case if cognitive processes can become a long-term stable part of a functioning planet, which implies a very different mode of interaction with the planet than is currently being exhibited by, quote, intelligent life. From a systems perspective, the early stages of that transition are arguably highly unstable because global influence precedes global control. And such a system is characterized by unstable positive feedbacks, which threaten catastrophe. And that's what I call our Anthropocene dilemma. We have global influence without global self-control. However, I do argue that conscious awareness and control can also be sources of stabilizing negative feedback. And there are a lot of examples that we can get into of that. This would require that we reach a stage where we have a deep understanding of nature and an ability to forestall natural disasters, as well as the deep self-understanding necessary to forestall self-imposed disasters. In other words, it would require both technical and spiritual progress. But once we get over the short-term threat of destabilizing fossil fuel-induced climate change, if we do get over it, then we do need to learn how to become a long-term stabilizing factor on this planet, which will include, over the next several hundred to thousand years, asteroid and comet defense, over the next several tens of thousands of years, learning how to prevent ice ages and other natural episodes of dangerous climate change, and then finally, over several billions of years, compensating for the warming sun and preventing the inevitable runaway global warming that would otherwise result from stellar evolution. So, briefly, it's also an interesting question that's relevant for SETI, the possibility that we can find sentient worlds. We're talking about looking for biosignatures. We might as well also be looking for technosignatures. So I think that it's conceivable, if this transition happening to Earth is a transition that can happen to planets, then there may be three kinds of exoplanets: dead ones, living ones, and sentient worlds. So, last point, as a climate modeler, and I do climate models, although mostly of other planets, but my view of geoengineering is that on the very short term, it would be folly to attempt large-scale solar radiation management because we are far too ignorant about the climate system. But I very much support the kind of research we've just been hearing about, although I'm skeptical about short-term implementation. But in the longer run, it will be our obligation to stop the Milankovitch cycle before there's another ice age, and to eventually learn how to manage, to intelligently and responsibly manage global climate. In order to do so, we greatly need to increase our knowledge of both the Earth systems and of ourselves. Thank you.
Well, we may not be the only session in which the Milankovitch cycle is being discussed, but I suspect we're the only one in which the possible control of the Milankovitch cycle is being discussed. All right, next, Jane Long will give some introductions.
American Astronomical Society had a position on geoengineering. And what got me concerned was the proposal to put sulfur dioxide particles into the Earth's atmosphere to make it cloudy all day and all night, which would be bad for people doing ground-based astronomy. We X-ray astronomers, we don't care, but the rest might be impacted. So so the concern or the question is, should the AAS have a position? And if we have a position, how should we come to that position? And I'm not going to tell you what the answer is. My own opinions are geoengineering is extremely dangerous at this point because we don't really understand climate all that well, or certainly I don't. One of the most impactful pictures that NASA ever published was a picture of the Earth and from the moon. And if you look at that picture, you realize we're on a spaceship. And if you're on a spaceship, if you have too many people doing too many bad things to the atmosphere in the spaceship, you're going to be in trouble. That's a fairly obvious statement. So the issues, if we're going to have any effect, always come down to politics. It's easy for us to say stop burning fossil fuels because maybe we can afford to build nuclear power plants. But overall, in the world, you can't just say stop burning fossil fuels unless you give people an alternative. Just my final comment in terms of sequestering CO2 into the ground, I like fizzy water. I'm looking forward to putting lots of CO2 into the groundwater. And so let's open it up to discussion, and thank you.
Is about the relative uncertainties. So we've been studying the climate for over a century, and yet there are significant questions that remain about how the natural climate system works. How do the sizes of uncertainties of the geoengineering proposals that you've already discussed just now compare to the sizes of uncertainties of our understanding? The size of uncertainties in the climate models themselves.
Everybody's looking my way. So this is sort of a half a class worth of lectures, and I'll try and keep it simple. The thing that we don't understand, I would say at the top of my list of climate, is natural variability. It is the coupling of an ocean with one time scale to an atmosphere with another time scale to a cryosphere with a third time scale, which produces internal oscillations. We have no ability at this point to predict those internal oscillations, the frequency of them, or the occurrence of them. A best example of that is the ENSO, or El Nino Southern Oscillation. Once we see it start, we can tell you what's going to happen, but telling you when the next one's going to occur is extremely difficult. We're talking about a forced system. Now, we will argue that our understanding of the force system is much better than our understanding of the internal variability. That remains to be seen, because we don't have a good history of predicting the force variability. I can tell you what I think is going to happen in 60 years. We'll have to wait to verify that forecast. One other thing that needs to be said in this context, so the uncertainties here are large in internal variability, but perhaps not as large in the force system. The other thing that needs to be said is there's a climate sensitivity. So if we apply a forcing, we're going to get some response. So if we apply a CO2 forcing, we're going to get some response that's a function of the climate sensitivity. If we apply a solar forcing, we're going to get some response. That's also a measure of the climate system's sensitivity. Now, if I assume, and this is a brave assumption, but we always get to linearize in the first approximation, that the sensitivity is the same going up as it is going down, then all I need to do is figure out what the forcing is from CO2, and I can compensate the forcing for the solar radiation dimming, and I can make those two match regardless of what the sensitivity is, because the sensitivity is the same on both sides. All right? So I think the uncertainties in some sense about the theory are not that great. The uncertainties about the application may be a lot more difficult.
Other comments from other panelists?
I think most people, when first faced with this, feel a lot more comfortable with carbon dioxide removal than with solar radiation management, because they feel like that's returning the Earth to its natural state. But I would caution that none of this is going to be actually returning to its natural state, and there is no natural state, and it's all a dynamic. So when you start talking about the massive amounts of 500 gigaton problem of the extra carbon dioxide in the atmosphere, you still have to talk about what you're going to do with it. It's not enough to take it out of the atmosphere. You have to put it someplace. And I think there's been a lot of work done on geologic sequestration. There's been some work on artificial weathering, which goes in the right direction, but is very slow. And in fact, I think in the end, in the time periods we're talking about, which are rather dramatically short, from that perspective, we're going to be talking about putting it in the deep ocean. And I think that's going to be a very, very difficult conversation. So, it's expensive to take it out of the atmosphere and slow, and then you have to put it somewhere. And just to add to what Tom said, I think we're talking, you have to think of this in terms, it was a good question, because you have to think of this in terms of a risk decision. I don't think you will ever get to the place where you would, I would feel, would be responsible to willy-nilly apply these technologies. Let's just avoid this whole problem. It's going to be because things are potentially going to kill a lot of people in a lot of ecosystems, and we're looking at that risk in the same case that anything we can do is worth trying. And that's the context. It has to be a risk decision.
Yeah, I agree with everything that's been said. I would just also like to say that I worry about our ability to really understand what's going to happen on the smaller spatial scales, the regional scales, that we can have a solution that basically works globally, gets our average temperature down to a safer range, but that if in some regional scale, if the monsoon doesn't come in one place, our model still might be doing a pretty good job, but that can still cause a disaster for a lot of people. And I know you guys are looking at this and you're aware of that. That's if I had an area of concern, that's my area of concern. And then also it needs to be reemphasized, I think, that if we just controlling solar radiation and we're not dealing with the other problems, CO2 causes like ocean acidification, which is worrisome. But I do like the way you're thinking that it could be sort of a temporary fix until we get the CO2 down. That certainly is a scenario that's worth investigating.
If you put it in the deep ocean, it will acidify the ocean.
Right.
Okay, I guess I can't resist one comment, which is it's all this focus on CO2, but you're not talking about methane, and you're also actually water vapor is a very significant greenhouse gas. So I hate to see the zeroing in just on CO2. And remember, every time you breathe out, you're making CO2. So we all need to cut down on breathing out, right?
Let me make an atmospheric point. Water vapor is not the issue. Water vapor is the single largest greenhouse gas in the atmosphere, but the amount of water vapor in the atmosphere is controlled by the temperature. If you change the temperature, you put more water vapor in. Decrease it. If you increase, you get more water vapor. If you decrease it, you get less. So water vapor will respond to what the other greenhouse focus on CO2 is because it's the single largest gas, and the point that Jane made, it has an incredibly long lifespan. If we stop putting methane in the atmosphere, it's gone in 10 years. If we stop putting CO2 in the atmosphere, it's still there already. So there's a reason why we focus on CO2 as opposed to the other gases.
That leads me to my next question, which is about timescales. So CO2 lasts for centuries, methane for roughly 10 years. What are the relevant timescales for the geoengineering proposals that have been floated? What if SAI, stratospheric aerosol injection, doesn't work and we decide to stop it? Will the atmosphere self-correct? What are the timescales for that? It's roughly 400,000 years for CO2 to self-correct. What is it for stratospheric aerosols?
Stratospheric, I don't think I'm saying time scales as David. Just as a side note, it's really interesting that David and I started our careers at the same place because I was also in geopolitics, both of us. But I don't think on those time scales typically we are focused on the idea of the next century in terms of these geoengineering ideas. If we stop doing sulfate injection, the stratosphere will cleanse itself in about 4 years. The e-folding time for stratospheric aerosol is about 2 years. All right, so about 4 years you've gotten rid of most of it. We have a pretty good handle on that, again, from some of the recent eruptions, like Pin 2. So it's not a huge long-term problem. If you do the moving top right that I'm interested in, you stop putting the aerosol in, it cleans itself in a week. So one of the things that actually, rather than worrying about getting rid of this stuff, when you think about doing this, you need to think about a continuous delivery system. You can't stop once you start. You can't take a month off. You can't take a decade off. You have to keep doing this because the temperature stability depends on this constant injection.
Just to reemphasize that point, so if you did stop, in a matter of a few years, you don't have the aerosols in the atmosphere anymore, but the temperature goes back up to where it would have been without any aerosols very quickly, which is really very damaging. So that's why I was showing that sort of strategic concept that you have to have, if you're going to do this, you need to be doing mitigation very rapidly, and you also need to be thinking about CDR and to do SRM, because you have to have a way to stop. You can't expect that, although David may disagree, we may be doing it for the rest of a billion years, but I think that basically there are no human institutions you can point to that last that long, so it would seem like you have to have a way to stop. And the only way to stop is to bring the concentration of CO2 down.
Yeah, I mean, I think it's interesting that, global warming itself creates unprecedented problem in global governance. Anyway, that's really what we're dealing with. And solar radiation management would itself be an unprecedented problem in global governance in response to that, because as you said, the rain-out times for particles are, in a few years everything goes back to normal. So once you start, you've got to keep doing it. As far as those longer-term challenges that I mentioned and Jamie alluded to, yeah, I mean, we have we're talking about a short-term fix here. That's what we need to talk about because we're in a crisis. But when I'm talking about interfering with the Milankovitch cycle, I'm talking about a much longer-term evolutionary process. But I think it's worth noting, and this goes back to one of Jane's points, that that everybody thinks that Earth that there's some natural state that's perfect. Not everybody, but some people think that. But that's an illusion born of the fact that our entire civilization has evolved in an unusual time in Earth history, an unusual period of relatively stable and relatively warm climate that will not last. So if we are to get to the point where we're able to solve these global governance problems and imagine that we will have a civilization that continues as long in the future as it's existed so far, depending on where you start, the civilizational timescale of 10,000 years, and another 10,000 years, or certainly in another 50,000 years, we'll have to worry about so-called natural climate change that would be very injurious, not just to our civilization, but to other species as well. And we can, once we get over our reckless current vandalism, we can prevent mass extinction and sort of flip and play a constructive role. But that's a much longer-term problem, and so I don't really, you know, that's a whole different discussion of whether we can get to that point. But what we're talking about here is our immediate problem, which is getting through this next century without global average temperature being 3 degrees warmer.
I guess just a non-expert comment is we heard about delivery systems. So one thing we better figure out is how much it's going to cost to deliver whatever it is. And as a person who's worked on satellites, at least intelligent, you know, technologically advanced satellite costs a lot of money per pound to put into space. Now, I can't tell you about dumb particles, but if you're continuing to launch rockets, rockets themselves cost a fair amount.
I'd like to turn to a question a little closer to the hearts of many people in this room. And of course, one of the issues astronomers have always cared about, in the last century anyway, is light pollution, artificial brightening of the sky, the quality of the sky and its effects on our ability to do research. A recent study by Charlie Zender at UC Irvine found that stratospheric aerosol injection at a level sufficient to counterbalance current anthropogenic warming would produce a brightening of the night sky in urban areas by about 25%, and a dimming of starlight with roughly twice as much starlight scattered in the atmosphere as currently. So how bad is this news for astronomers? The difference between light pollution and stratospheric aerosol injection being, of course, that light pollution has no benefit, whereas stopping global warming obviously does. So this is not to equate the issues, but to try to understand.
I'm going to make a statement that might be unpopular in this room. Fixing global warming is more important than astronomy. Now, I say this as a lifelong astronomy enthusiast, and even though I'm a theorist and a planetary scientist, I have done some observing, and I very much am concerned about light pollution. But, you know, and I don't think we're at this point, but if we were pitting the potential displacement and deaths of many people and extinction of many species against our ability to do ground-based astronomy for some decades, then to me there's no contest. I don't think it's come to that, and if anything, this gives astronomers a reason to not want it to come to that. But also, if it does come to that, as we've heard from Tom and from Jane, that it could be seen as a temporary fix until we get the carbon dioxide down, and that would certainly create incentive among the astronomy community to devote ourselves to that next phase where we don't have to use aerosol injection. So I don't think it's going to come back, but there's no question to my mind that you know, saving our civilization and many other species is more important than our ability to do ground-based astronomy for a few decades.
If I were still capable of doing good science, I would have run off some calculations, because I did think about it when I saw Charlie's paper. I think Charlie's calculations were done for the equivalent of 2 times CO2, which is not where we're at yet. And he took the amount of solar radiation dimming based on an aerosol model. You'll get different answers. Also, this is a calculation that's done as a flat plate, and as you're all well aware, astronomers, the Earth and the Earth atmosphere are flat plates, and they're not homogeneous. And so there's some issues here about what the brightening is as a function of the angle that you're looking at. It's not uniform in the sky. Nonetheless, there's no doubt that if you put up stratospheric aerosol layer, you're going to create scattering, and it will in fact influence your ability to ground-based astronomy. When James first contacted me with this sort of idea, the first thing I said was, Just guessing. I'm only and last, you should probably support what I'm doing then, because we're talking about brightening the green clouds, and they'll have no effect on the astronomers' view of the world.
More comments from the panel? I want to ask a question from the audience. Sorry, Jane.
Just a number of the cost. The costs, I don't have the numbers at my fingertips, but the costs for SRM type technologies have been calculated by people based on airplane distribution or terrestrial distribution and whatnot, and there's certainly within what's possible given the world's economy. It's a small fraction of what's CDR, on the other hand, might be more expensive.
Want to define CDR?
Oh, sorry, carbon dioxide removal might be more expensive.
Which leads to my question, first question from an audience member for David or Tom, or I think anybody who's fair game here. If we require an exit strategy of CO2 removal, why introduce the highly uncertain geoengineering? Why not go straight to the exit strategy?
Yeah, go ahead, James. Go ahead.
Yeah, I mean, I think I tried to explain that, maybe not as clearly as I should. The fact is that mitigation is the primary strategy. There's no question about it. But it's going to be very difficult to achieve the targets we need to achieve to stay below the temperature targets by the end of the century. I think that both the willpower and the technology are not there. I've done calculations for the state of California, which you would think would be the easiest. Emissions in California have not dropped in the last decade. They have not dropped. They went down during the recession and came right back up. We are not on a trajectory to get 80% below 1990 levels by 2050, which is the state's policy. This is not an easy thing to do. It's going to require a serious commitment to deployment and to changing policies. And plus, we have no agreement on the international level to any of the needs. We have only some agreement now on a goal, which is fantastic. But that means that each of these regions are going to try to do it on their own, which means that they're going to leave their problem. The city of San Francisco is my favorite example, where they said they would have no more carbon dioxide from their electricity system, and the way they were going to do it is stop selling their hydropower to other cities. And so they just caused other cities to burn gas. This is the kind of thing that's going to happen. It's very difficult to come up with the mores and the rules for the economy so that all these regional programs will add up. I think the idea that we're going to be able to hit this target of mitigation by mid-century is a myth. We're just not going to be able to do it. But we need to try. We need to try as hard as we can. And to the extent that we miss it, then you start to think about this emergency response if things get really bad, which is what SRM is. And if you are not pulling that stuff out of the atmosphere at the same time, you have no exit strategy for the SRM. And so the whole thing has to come together as a toolbox. And whether or not we use these technologies really will depend on how bad the impacts get. One other comment. Because this response is regional, the whole idea that we would have some global institution that is going to globally enact and deploy geoengineering is probably is also very distant and very hard to conceive of how we would come to that conclusion. But what is not hard to conceive of at all is regions taking actions to mitigate not in the sense of the old sense of mitigation, but in the English use of the word, mitigate their impacts. So people will try to steer monsoons, and they will try to rain out clouds, and they will try to do things to mitigate heat waves on a local basis. These actions, as they become larger and more long-term and more forceful, are going to add up to perturbating the entire climate of the Earth. And that is almost certainly going to happen without anybody being able to control it. So this research needs to be going at both ends. We need to be looking not only at these global ideas, but how the local things are going to add up to things that end up changing our climate. And it's a very, very complicated problem. We're not putting anywhere near enough money into
asking me which one of these technologies is going to show up as the right technology, I have no idea in some sense because we're not doing the research, as Jane said. I think if you ask me which one is the physically most understood, it's stratospheric aerosols. And that's because the stratospheric aerosol system is relatively straightforward, and we have volcanic eruptions that we can use in some sense to calibrate our understanding. I'm working on the marine brightening side of this, which is much more complex in the sense that you have to understand what happens when you inject extra aerosol into a cloud. So there's a whole bunch of wet thermodynamics that gets, pretty interesting. But it has the advantage of being much more targetable than stratospheric aerosol. So I don't know which one's going to show up. I don't know if we can do either one with any sensible knowledge at the moment because we don't have any experimental base to draw on.
There's a kind of geoengineering, by my definition, which I'll state in a minute, that is already underway and I think will be greatly enhanced by 2050. Imagine an invention that could pull carbon out of the air using solar energy and use that carbon to create energy or fuel. Wouldn't that be a marvelous invention? Well, of course it exists. It's called a leaf. And in my view, reforestation, not just reforestation, but enhanced and artificial photosynthesis is a kind of geoengineering that's already underway and limited to a limited extent and must be and will be increased. The reason why I say that's a kind of geoengineering, in my book, and I actually have a book about this, the crucial difference and the threshold we need to cross is between inadvertent tinkering with the planet and purposeful tinkering with the planet. And we've already done some of this purposeful tinkering with the planet. There are plenty of existence proofs. Look at how we've dealt with the ozone problem. So we have it within us to do this. And by that, and I call this, I developed this a little bit more, I call this planetary changes of the third kind, which are inadvertent changes, and planetary changes of the fourth kind, which are purposeful interference with the planet. If you accept that distinction, then anything we do that is intentional on a large scale that changes the climate is a kind of engineering, and that even includes mitigation of our CO2 emissions. If this is a broad effort, then we're purposefully changing our interaction with the planet as opposed to the inadvertent vandalism we've been doing. So I think that reforestation and enhanced and artificial photosynthesis are very safe and important and necessary ways to do a kind of relatively benign geoengineering that will become increasingly important.
I'm afraid that reforestation will not solve the problem.
Yeah. I'm not saying as a single cause. I'm saying as a component.
I'm perfectly happy with reforestation. One of the questions I pose to my climate classes is I give them the amount of carbon that's produced by the United States, and I ask them to figure out what fraction of the land surface of the United States you have to plant in trees in order to take up that carbon. It's a staggering number. It's like 2/3 of the area of the United States. On top of that, that forest, if you assume numbers that are uptake for a growing forest and not a mature forest, which isn't actually taken up that much CO2, you have to log the dang thing about every 25 or 30 years to start over again. And you have to figure out what to do with all the logs that you just took out of the ground. Some of this can be sequestered in the soil, but there's just not a lot that we can do. I'm all in favor of reforestation, don't get me wrong, but it's not going to solve the problem. People have looked at iron fertilization of the ocean. That's a different problem. It's a nasty problem to figure out if you can actually do it, and there's some real issues about whether you want to cause algal blooms in the ocean or not. So, in some sense, fooling around with biology is worse than fooling around with physics. At least physics is, constrained by some laws
next question is a combination of two from the audience and one from me. So the question from me was going to be, does investing significantly in research on geoengineering give politicians and policymakers a false sense of security and remove urgency from efforts to reduce greenhouse gas emissions and mitigate global warming? First place, two questions from the audience were, do you think COP21 goes far enough in terms of the resolutions put forth by participating countries to avoid runaway warming? And what can be done when the people that make policy don't believe in the science?
I think with regard to the first question, it depends on how we talk about it. And I don't think anybody would listen to what Tom or Jane had to say about geoengineering and come away with the thought, oh, this is no problem, this CO2 stuff. We're just going to solve it. This will be easy and everything's fine. I think if we talk about the emergency that we're in and how these may be desperate measures, but that we're aware of ways in which the cure could be worse than the disease, then this is part of the discussion that needs to happen, and is part of that larger discussion of stressing to policymakers and to citizens and voters that that this is a very serious problem. So I don't worry about it. I mean, I have seen some communication about this topic where that aspect is stressed. Oh, don't worry, we'll just fix it with some high-tech gee-whiz solution. But I don't think the kinds of talks we've been hearing today about this are really promote that view. And I think this is, it's just a way to responsibly keep our options open.
The question that James asked is referred to by my ethics colleagues as the moral hazard. You're creating a moral hazard in people by giving them an option to do something other than the right thing they ought to do. Jane and I would both argue, and I know because we've had this conversation, we would both argue that the best thing to do is to stop emitting CO2. And I always want to get that in. That is what we should be doing. The question is, what do we do if we're not doing it? To argue that we should remain in ignorance because we don't have enough money is a false argument. We're talking about trillion-dollar economies, and we are investing nothing. If you were talking about managing the risk, then what you want to do is develop the data in which to use to manage the risk. And say, oh, if I develop the data to manage the risk, I will then not manage the risk is a silly way to think about the problem, frankly. If I'm an actuarial science, I go out and figure out how often people die. It's not that I want people to die, I go out and figure out how often they die because that's what my life insurance policy pays off for. I would not think of writing life insurance policies without the data. So why do we think that we should not do the research, and yet we want to talk about this as a possible solution? The hoax question, I knew was going to come up sooner. Years ago when I was doing nuclear winter and I used to go out and give talks, I had this wonderful little cartoon I used to put up. And the little cartoon was this little Ziggy guy looking up at the sky at an angry star, and Ziggy saying, I'm not responsible for what Carl Sagan says. All right? And I used to feel like that. I'm not responsible for what Carl Sagan says. Well, I'm not responsible for what Donald Trump says either. I'm a scientist. I can speak to you about science. I'm not a political scientist. I'm not really that crazy about having a discussion about how climate scientists should be better communicators. I think that's a great subject, and we can go off and have that conversation. I don't think we're the problem. I don't think the fact that we're not good communicators, and I don't even think that's true. I can point to my friend Catherine Hayhoe, who's getting all kinds of good press, and rightly so, for trying to communicate with folks who don't think that science actually matters, and the landscape is not changing. I think the landscape will change, and it will change when those of us who look like me die off. Because the young generation gets it. The older generation is dragging its feet, kicking and screaming. So we may have to wait for that generation, what Jane and I will say is too long.
So I'll just take off a little bit of
just make a comment about the politics. Many years ago, I was at an Earth Observing conference. Don't ask why I was there, but never mind. Anyway, what came up from the NASA people that were there was, this was during George Bush II's administration. He cut off all funding for measuring what the CO2 content was in the atmosphere. And the point is that our presidents do have a direct effect on this whole area of research. And it's, to me, kind of scary. I mean, the idea was, well, if you don't know if you're gaining weight, then why worry about it?
I want to ask one final question before turning it over to members of the audience who haven't written down their questions. And that is, does the precautionary principle apply, and if not, why not? The precautionary principle is widely invoked in European countries. It essentially states if there is an action with uncertain consequences that may or may not be serious, wouldn't it be, isn't it ethically right not to take that action at all? So my suggestion is maybe if we were having this discussion with a panel of Europeans, you would be giving different answers.
No. The precautionary principle is, in the simplest form, which does a lot of damage to it, is do no harm. Okay? However, we are already doing harm. Right? So we're in a different form of the precautionary principle. And one that actually is pretty complex. And I can point you to some papers that have been written on it, which I've tried to read, some of which I understand. The point is that if we don't do something, harm will be done. All right? Because climate will change because it's warming. If we try and cool the planet to prevent that warming, we may in principle do other harm. All right? So what we're really talking about is not the precautionary principle. We're talking about a different problem, which is the lesser of two evils. Okay? So now you get into a wonderful dilemma of, is it right to do lesser evil? Is it right, this is the thing, if you've done anything, astronomers love, ethicists love to kill people. This is how they dramatize their solutions, is by killing people. So this is the trolley. Do I kill 100 people or do I kill 10 people? If the 100 people were unintentional, but the 10 people were deliberate, is it worse to have killed 10 than 100? We could argue about this for a long time. So the precautionary principle is not the principle we're talking about. We're talking about the lesser evil principle, which is a lot more difficult than the precautionary principle.
In some way, you can think of taking precaution as reversing some of the impacts of climate change, and that's precautionary. I think the precautionary principle is one of the most conflicted, misinterpreted, or not misinterpreted, but multi-interpreted. Everybody interprets the precautionary principle in a way that they feel supports their position, and it's largely, I think, something that makes an argument about the precautionary principle instead of about what we ought to do. And I think the issue here is about taking responsibility. I think that's where David was coming from, and fundamental to what we're talking about here. We have to enter an era of taking responsibility. So if you want to get into the ethical issue about this, I think the big ethical divide is between intentional act and unintentional act, the difference between manslaughter and first-degree murder. The issue is how, at what point, and in what ways do we learn how to take responsibility? And the precautionary principle was fundamentally, in its origin, about taking responsibility.
Anything else? Thank you. I'd like to open up the conversation to the floor now. So who in the audience has a question that you'd like to ask, please use the microphones.
So this has been a very good session, lots of good information on there. I teach first science for non-science majors, resource. And one of the things that I've tried to talk to the students about, both in terms of climate change but also just other natural disasters, is about preparation and adaptation. Things happen. And from what I picked up on here was no matter which of these strategies you're going to do, that there's going to be some change in climate, especially regionally. How do we get across the message to people that parallel to all of this research that needs to be done, that we need to do research on how do we adapt to climate change? How do we get crops that grow when there's less moisture or stuff like this? Because I'm finding, especially in American society, people don't adapt well to changes. They want everything to be exactly the way it was, and even if we employ the strategies, things won't be exactly the way they are. So what are your thoughts on having the parallel message of adaptation as well as the mitigation?
It's funny that there's been an argument about this. It's a great question you asked. There's been an argument that parallels the argument that was raised earlier that we shouldn't be talking about these intrusive geoengineering fixes because that might give the impression that we have less to worry about. There's also been an argument that one has seen that if we put resources and attention into adaptation, then we're giving up and accepting climate change, and therefore that's to be avoided. But as Jane said, we have to tell the truth and figure out what the truth is and tell the truth. And the truth is that, as you said, there is going to be climate change. There are going to be more and changing natural disasters. It's going to affect our agriculture, our ability to our aquaculture and so forth. And yes, so absolutely, in parallel to our efforts to mitigate global warming, we have to. The responsible thing is to try to understand the changes that are already set in motion and do our best to adapt. And it's not an either or. In fact, it's very much a both and. We need to be doing both.
We need to be doing it all. I mean, I believe this is an existential threat, and I think you are going to need every tool you have in the box. And certainly all the adaptation tools you can come up with are going to be important. I also think that the lines are going to blur between mitigation, adaptation, and geoengineering. As the tools, I think there are going to be things that come up at the interfaces, and then one will roll into the other. I don't think there's such. People talk about BECS, for example, which is biological energy carbon sequestration. Some people want to call that a mitigation tool. Other people want to call it a geoengineering tool. I don't care. Less carbon in the atmosphere.
I think, unfortunately, the American society is willing to go on with blissful ignorance. And there are places in the country where adaptation is taking place. Miami is going to have to adapt to rising sea levels, even if the state of Florida says you can't consider climate change. It's going to have to be done, and it is being done. You can go to Europe, and you can see what the Dutch are doing, what the Germans are doing, what the English are doing, to talk about sea level rise and river tide backing up the river and that sort of thing. So adaptation is certainly a part of what we have to do. It's really hard to figure out how we adapt, however, to long-term drought. There's not really an adaptation strategy for long-term drought other than to move people. So some of the adaptation are going to require dislocation. If we're going to drown out Pacific islands, who are going to take those people in? Are we willing to commit to taking in 10,000 survivors from Tuvalu or 30,000 survivors from Kiribati because they can't live where they live anymore because of sea level rise? So adaptation is going to be both political and sociological and massive.
Don't forget economic. I mean, I actually think that one of the biggest issues in adaptation turns out to be financial vested interest. And that is going to be something you're going to have to figure out how to deal with.
mentioned the Dutch and sea level rise. If you want to think of an example of a society that has taken a long-term successful approach to a large-scale engineering problem upon which their existence depends, and have thought about it on the long view and absolutely committed as a society to successfully solve both the engineering and the governance problems to deal with what would otherwise be an existential threat. Look at the way the Dutch have dealt with sea level and are planning on dealing with sea level. It's existence proof of a kind of approach and solution. And who's to say that if they can do it nationally, that we can ultimately learn to do it globally? People get very attached to thinking that human nature is this immutable thing. But remember, we were once hunter-gatherers, and the idea of a modern city to somebody who was a hunter-gatherer would have been maybe as unimaginable as it is for us to try to imagine a truly globally sustainable society. And of course, when we first moved into cities, they were horrible places. And then we discovered sewage systems, and that made a big difference. So now we need to discover the sewage systems of the 21st and 22nd century.
We're very close to the end of our time, so let's say two questions, and let's try and keep the responses quick so we can get these two questions out of folks.
All right. Hi. I'm curious if there's been any conversations between geoengineering and goals such as terraforming as a means of funding this research, because there are private industries such as SpaceX who have that as their final goal. So that might be a means of funding this research. Have there been any conversations between those separate interests?
There's been a lot of talk between the communities, and a lot of the people, as I mentioned briefly in my talk, a lot of the people that were talking about terraforming in the, even in the 70s and 80s were some of the first people that started talking about geoengineering, and certainly intellectually there's been a lot of crosstalk between that. The problem with getting, I think you were hinting at maybe getting financial support from somebody like SpaceX for this. The problem is nobody's making money or even really imagining making money from terraforming. Even Elon Musk isn't really. So it may be somebody like that who has a lot of resources and just thinks it's a cool enough and good enough idea to help support this kind of effort. But I don't think it's really a way to monetize. There's no really way that anybody's envisioning monetizing terraforming.
Nor would you really want to. I mean, I think that's fraught, very fraught, to have the idea that someone with a financial vested interest would be controlling what happens to the global climate. It's scary. Yeah, indirectly, but not directly.
Final question from you.
So I wanted to return to the situation in the Netherlands, which David mentioned just a few minutes ago. And the concern I have is that the Netherlands is a very small country, and there's a question of scaling it up. And then the second question is that we're now at the point where just one country, even one as large as the U.S., can't do it alone. So I wonder if any of you would like to comment on that.
That's actually not true. It depends on what it is. It's perfectly possible for the United States or many countries, probably a dozen countries around the world, to implement and deploy anti-solar radiation management technology. And actually, one of the reasons for doing research is to protect yourself against that. I mean, I was in a meeting in Washington a few years ago with some discussion about China and this topic, and people after discussing and hearing talks, how many people in the room think that China will try to do this, and everyone raised their hand. So I don't know if that means anything, but I think the question is really, how do you do it right? How do you do it with governance and then not have a single country take
go back to the analogy of the Netherlands, there's a couple things I'd say. First of all, you're not going to scale the Netherlands to the United States. Population densities are different. However, the point that Jane made earlier is really relevant. We have got to quit supporting people who live on the North Bank, the Outer Banks of North Carolina. All right? We can't protect them, and we can't keep bailing them out every time a hurricane hits. That just makes common sense. The Dutch have decided what they want to protect and what they don't want to protect, and I think that's the real decision. Not that we're going to make the United States look like the Netherlands. What do we think we need to protect, and how much is it going to cost, and do we have the will to do it over the next 20, 30, 40, 50 years? The Dutch have been doing this for a long time. They're in this for a long time scale, and we don't make that commitment in the United States. So I don't think it's a matter of scaling up the whole Dutch experience as much as it is scaling up that culture and saying, this is something that we have to fight with every single day. I was in Delft a number of years ago, and they had a big flood, and they didn't adequately prepare they had a big rainstorm, they didn't adequately pump down the system, and there was a lot of flooding. The guy in charge of the water district got fired because he didn't adequately prepare. Right? That's a different philosophy than what we're operating with right now.
Just to bring up again these, the 3 R's of adaptation, which I now remember: resist, retreat, and resilience. And the one where the research community really needs to play is in resilience. How can we become more resilient, have better crops, have more flexible housing that survives fires, whatever, all these issues that you can work on from a research perspective. But the resist and retreat issue is being managed extremely well in countries like the Netherlands and not as well here. So I think that basically we're doing it haphazardly. The population of New Orleans has not come back. It's like 50% lower than it was before Katrina, and that is retreat. That is exactly what happened, but we did it in a way that harmed the most vulnerable people in the population, part of our population, and we did it in a way that was cruel and unusual. So I think basically, I agree with Tom. It's these retreat decisions that are really important, and deciding what you're going to harden. Where are you going to throw those precious dollars to harden the landscape so that it can survive these episodes?
We are at the end of our time. Please, everybody, thank Jane. To be continued. This has been a most stimulating and eye-opening conversation for all of us out there. So let's keep the conversation going.
It's great.